If you're into drinking wine and determining flavor profiles by just looking at wine glasses, one of the techniques used is to look at how much light passes through a glass of red wine, for example. And wines that have much heavier bodies and much bigger flavor profiles, like Zinfandels, will appear to be much darker than lighter wines like Pinots. And I think this is kind of a cool introduction and segue into the way spectrophotometry works, as well as the Beer-Lambert law. And so essentially what we can do in biochemistry labs, for example, if we wanted to have a convenient and quick way of determining the concentration of proteins in solution, is to use spectrophotometry. And the way it works is if we have a light source, like a light, so a light source, and we shine it through a monochromometer. This is a bit of a tricky word. Monochromometer. All this does is essentially filters and isolates one wavelength of light, one lambda, and then shine that through a cuvette, which are typically transparent little plastic things, and they have a path length very commonly of 1 centimeter. If we then analyze if we then place a detector behind the cuvette detector, we can very easily figure out what is the concentration of your solution inside your cuvette. And so to start out defining some terms here, we will have some intensity of light I naught that is incident on our cuvette, as well as a transmitted intensity I that is leaving the cuvette. And so the more stuff that's in this solution, the more light will be scattered out as the light tries to pass through it. And so the denser our solution is, or the more concentrated it is, the less intense I will be. And so what the Beer-Lambert law tells us is that the natural log ln of I over I naught is equivalent to something referred to as the molar absorptivity coefficient epsilon times B, the path length of your cuvette, which is very commonly 1 centimeter, times C, the concentration of your solution. So that's concentration of the solution, path length, and the molar absorptivity coefficient. And in practice, what we'll do commonly is have to make standard curves in order to correlate the concentration with the absorption. And so another thing that's very common to do is we will lump these three quantities into a single variable and call that A. And A is the adsorption, or adsorbance. So how much light is absorbed by your solution, and A is proportional to the inverse of T, transmittance. And so transmittance is an indicator of how much light actually makes it through the magnitude of I. And so a very important thing to consider when we are analyzing the Beer-Lambert law is the dimensions of all of these variables. And so we'll note how the intensity of light has units of watts per meter squared, just like a sound wave intensity, decibels. Epsilon, the dimensions on this epsilon variable will be dependent on what dimensions we choose for concentration and path length. And so B will have units of length, And C, sometimes it will have units of moles per liter molarity. Other times scientists will use things such as grams per cubic centimeter. And so it's very important to check the units before continuing on any Beer-Lambert question you come across. Otherwise, you might get, or you will get, bad results. And so the other thing to note here is that because the left side of this equation is a dimensionless quantity, the right side of the equation must also be dimensionless. And so if you can keep that in mind while you're solving these kinds of problems, you'll do well. And to give some more background on this, so when we develop our standard curves in practice, what we do is we analyze the absorbance, A, versus the concentration of your solution. And we will get an initial linear region, an initial linear relationship between A and concentration, and the slope of this will have a value corresponding to epsilon, which was our molar absorption coefficient. Now, it is important to note one con with the Beer-Lambert law, and that is at very low concentrations and at very high concentrations, we no longer observe linear behavior. And so when we have absorption coefficients, absorbances less than 0.1 or greater than 1, this linear relationship that we have in this region goes away, and we can no longer use this relationship. But most of the time we are able to get away with it, and it is a very useful tool that allows us to quickly determine a protein concentration, for example, in a solution. And so this concludes how we use the Beer-Lambert law in spectrophotometry, and I hope you guys find this useful. Let me know if you have any questions, and thanks for watching.